All right, babes, a lot of meat and potatoes in this section, but we now have all the variables of motion from distance, displacement, speed, velocity, and acceleration, as well as time. So now what we're going to do is we're going to start to try and understand the different types of motions and how everything are connected through different types of diagrams. So all this section we're going to focus on the different ways in which we can represent motion. So there's going to be a lot of meat and potatoes, so if at any point you got to pause the video, write some things down, go ahead and do so. So the first type of diagram we're going to look at is what's called a dot diagram. So a dot diagram is literally what you see in these pictures. We're going to make use of dots. And the dots, think of this as almost like a number line, where you might have seen in math class to say I got a number line that looks something like this with, 0, 1, 2, 3, 1, 2, 3 in the negative realms. A dot diagram is going to locate our position of an object that's moving. It's going to locate the position of that object through certain points of time. So let's say an object starts right here, and then 1 second later it's right here, and then 1 second later it's right there. And by looking at those, we kind of get a sense of the different types of motions. So for example, we can figure out its distance, its speed, its acceleration. We can figure out, okay, is it moving at, let's say, a constant speed? Maybe it's accelerating, where maybe it's either speeding up if it's going to the right, or maybe slowing down if it's going left. Maybe that acceleration is different, right? We can see the different things. And obviously you can see based on the dot diagrams, we're going to focus a lot on the spacing of the dots, and that's going to give us really a good sense of what's happening. So all we're doing is really looking at its position values, but that gives me a sense of what the object's motion is. So in this first example, what we're going to do is just see if we can try and look at a picture and understand what the object is doing. Okay, so kind of using some words here. So in this first diagram, I have a car moving to the right. So I know that I have a rightward moving object, and we see that the dots are spaced out. And when we look at the spacing, we can see that the spacing between the dots is the same every time. Now, if it means it's the same, that means this object is going to be moving at a constant speed. So I'm going to say this. The object is moving with a constant rightward velocity. I'm going to use velocity since we're indicating the direction. It's moving at a constant rightward velocity. Versus in the second graph, our second diagram in B, we notice now just based on what the car is doing or which way it's pointing, we obviously know it's not going to the right anymore, but it's going left. And again, if we look at the spacing, we see, okay, large spacing gets a little smaller, gets a little smaller, a little smaller. We'll see that the spacing between the dots is getting smaller and smaller. So in that case, we know that it's not moving at a constant speed anymore, but we know that it's slowing down, okay? So first of all, we know that this object is a leftward moving object, and we know that it's slowing down. And the last thing is, because it's slowing down, that means it's accelerating. So the thing I'm going to connect is what we talked about in our last section with acceleration. If it's moving to the left and slowing down, that means it has a rightward acceleration. I want to bring that up because we might see some of these words being used as we go through. All right, in C and D we have multiple parts here. Okay, so obviously we can see that the object is moving to the left. So let's say it started all the way over here. Notice the dots. If it started here, notice the dot spacing is getting larger and larger. Therefore, I know that in part 1 of this motion, I'll just label this as a 1, we know that it's speeding up, right? Because the dots are getting farther apart. Now, if it's moving to the left and it's speeding up, I know that it's experiencing a leftward acceleration, right? In this case, I'll put in parentheses, it is speeding up, okay? Second part of motion, you'll notice all these dots are kind of gathered right here. So obviously it changes. It does something right here. So if at any point we see dots kind of stacked on top of each other, that means that this object came to a stop. I'll just say it stopped for maybe a second or two. And then the third part of the motion, we see it's still moving to the left, but notice the dot spacing is the same throughout. So then I could say it's moving here at a constant leftward velocity. Now notice as I'm doing this, I'm using keywords like the direction, right or left. I'm using the words acceleration, velocity, and all that to kind of explain what's going on with this motion. All right, I want you to try this in D. In D, you got 3 parts again. So let's see, can you figure out what's going on in D? I want you to write what's going on in those 3 parts. So give D a shot. All right, so here's what I got. Moves first with a constant rightward velocity. Here we see the dots stacked, so I'm going to say it stops and changes direction because we see now that the car is going towards the left. So it's constant leftward motion because of those dots spacing. So this is using diagrams to kind of understand, again, dot diagrams. By looking at the spacing between them, we get a sense of what's going on and understand how the object is moving. All right, next type of diagram, which is related to the dot diagrams, is a vector diagram. So a vector diagram is going to look very similar to the dot diagram. Key thing here is a vector. So a vector diagram is going to make use of, as you can see here, arrows. And these arrows are going to represent the velocity of the object. So anytime we want to represent something that is a vector, we're always going to use an arrow to represent it. So in this case, we're going to represent the object's motion by tossing in some arrows. So it's very similar to the dot diagrams, but the dots only showed where it was, its position. Now we're going to throw in arrows to show acceleration or velocity, all the other different variables we could have. All right, now similar to a vector diagram, once we combine the whole idea of its position and where it is and how it's moving, its velocity, and then whether it's speeding up or slowing down, its acceleration, combine all those things together, we get what's called a motion diagram. So a motion diagram is kind of what you're seeing here in this little video. It's showing just an object that's moving down some track, a little ball here, but think of its position as where it is, but you'll notice the velocity arrow, the green arrow for the acceleration. It's showing you all the different components of the object's motion. So once we combine the dots and the arrows, we get ourselves a full motion diagram. All right, so showing that here, we're going to do a motion diagram for a rightward moving object. In this case, all we're going to show here is the velocity vectors, okay? So we have a rightward moving object knowing it's going to go from here to here. To draw a motion diagram, I already have the dot diagram shown, so we know that those are the positions of that object. What's the motion like? We see that the dots are evenly spaced. So based upon that, I know that it's moving at a constant velocity. Now to show this, I'm going to use a blue arrow to show the velocity here. To draw the arrow, I'm just going to draw the arrow from one point to the next with my arrowhead right at the start of the next dot. And then I'm going to draw my arrow again. And again, between every dot, I'm going to draw my arrows, and I'll just skip that last one, although I know it would continue to move. And again, why is this showing constant speeds? If you look at my blue arrows, they are all the same length. So this is, again, showing constant velocity. They are moving in the same direction, and because of the length of the arrow, moving at the same speed. Whereas in B, drawing the velocity vectors again here, you'll see that the spacing gets smaller. So again, if I just draw my arrows here to represent the velocity, notice that my arrows are pointing in the same direction. I know it's moving to the right, but now you'll see the arrows slowing down, so I know, you'll see the arrows getting smaller, so I know that this object is slowing down while moving to the right. Okay, now we can connect those same kind of ideas, but now throwing in the acceleration vectors, okay? So acceleration vectors I'll show in green. Now I'm going to connect this. We just did this one for a rightward moving object. With the blue arrows, we showed its relative speed or velocity. Now in this case, notice how the arrows are the same. So I want to draw this with the acceleration vectors. If an object is moving with a constant speed like we see here, my question for you is the object accelerating? Acceleration means to speed up or slow down or change direction. We don't see any of those cases here in this diagram. So that means in this case, there is no acceleration. So one thing to bring up is that if we ever see constant speed or constant velocity automatically means right away that there's no acceleration. Okay? Now this next case, similar to the last one, but you still have a rightward moving object. If I draw my blue arrows to represent velocity, now I see that those arrows are getting longer, which means that this object is going to be speeding up if it's moving to the right. Okay? Now speeding up means that the acceleration is going to be pointed to the right. So what I'm going to do is I'm going to draw acceleration vectors on this diagram, okay? Now here's the way I like to think about it, all right? Is you'll notice that if I look at the spacing between the boxes, see how it goes from 2 to 3 to 4 to 5 to 6, So do you see how it's gaining a box every position? So the way I'm going to do this is because it's gaining 1 box every position, I'm going to draw my green arrow. Oopsies, wrong position there. I'm going to draw my green arrow above every dot, but I'm always going to draw it the same length. So notice how my green arrows are always the same length. They're constant, and the reason why is because I am gaining 1 box every time. It's +1, +1, +1, +1, and so on and so on. So my acceleration here is going to be constant. Here I have a constant rightward acceleration, but what that results in is the object to speed up. So even though its blue arrows are getting bigger, it's getting bigger because that green arrow is being added to it every second. It's a little tricky once we get to acceleration. All right, and the last nugget here we're going to go through is reading graphs. Okay, so we have the diagrams. Graphs are the same thing as a diagram, but now we're adding time into this because on those diagrams, time, we just represent it as a different point. So now we're going through continuously what's happening with time. So you'll see here, my position is represented as the y-axis, and time is represented as the x-axis. So down over here on the middle of this graph, this is when we're starting with a position of 0 and a time of 0. Okay, our origin. And what we're doing is we are moving forward in time and we're tracking our position. Okay, so what we're going to talk about is being able to read these graphs of position versus time based on an object's motion. So our first example is we're going to try and figure out based on this graph what the object is doing. Okay, so I have 5 stages here labeled A through E. And I want to know which of these represent the object being at rest. So at rest is the key thing here. At rest means that the object is not moving. Okay? So what does that mean on a graph if an object is not moving? Not moving means that its position is where it's located. Its position should not change. So where on this graph does it show an object's position staying the same as time moves on? And you should hopefully see that in B and D, those are showing an object being at rest. From A, it's showing an object moving in a negative direction. It's going downward. Now, don't think of this as up and down, but this could be moving south, could be moving west, could be moving left, could be moving down. C, that's also, now it's going downward, moving in a negative direction, so again, same thing. But now also in E, notice how the graph goes upward. So that means that E, the object is going the complete opposite direction, is moving towards, in a positive direction, so towards the east, north, up, right, whatever that may be. Okay? Now, next one we're going to throw in from a position versus time graph, how do we represent an object's speed? Ooh, so this one wants to know in which stage does the object have the greatest speed? So how do I determine speed in this case? Well, speed is going to look at your change in position over time. So remember, speed in general, speed is going to be the distance traveled in time. So if I want my speed to be the greatest, here's what I want. I want a large distance, and I want that to happen very quickly. So if I want a large speed, I want a big distance and a small amount of time. So which of these chunks would represent the largest distance traveled in the quickest time? And hopefully you recognize that A would be the largest speed because it has the greatest distance covered, goes from the positive all the way to negative, and the time is very short because you'll see it's just looking at this chunk of time right here, okay? One thing we are going to talk about is that in terms of speed, really what I'm looking at, if you think of that line, is something you learned in math class, whoopsie daisies. This is called the slope, babies. Whoa, calm down. All right, that goes into our next examples, babes, is using those same graphs to try and figure out the speed and velocity, or speed or velocity. So in these two examples, all we're going to do is rank the speeds from slowest to fastest. So I have here this first example, 3 lines drawn, A, B, and C. They all start at the same point. So they're all starting right here. They're all going, in this case, in a positive direction. All those lines are sloped upwards. So in order to rank the velocities, what we're going to simply look at here is the slope of the line. The slope represents the steepness, and the steepness is going to tell me the relative speed. So if I think of these three lines, the one with the greatest slope is moving the fastest, and the one with the smallest slope is moving the slowest. So if I were to rank these, it's pretty simple to see from slowest to fastest. It would be C, B, and A, because C has the smallest slope, A has the largest slope. B, a little bit sassier now, because we have not only lines going in different directions and starting at different spots, we also have some lines going up and down. So a couple two treat things here, folks. The starting point does not matter. So I got one starting here, one starting here, one starting here. You also see some lines going up, like A is going upwards, and you'll notice that B and C are both going downwards. So when you see lines going up versus down, all that simply has to deal with is the direction in which it moves. Direction has nothing to do with the speed. Direction just has to deal with the direction it's moving, okay? So in order to look at speed, again, all we're going to do is look at slope. So for example, we have A, B, and C. So when I look at the slopes, I want to find the steepest line. And I can probably see that based on, even though A is going upwards and these are going downwards, I can see that A is the steepest. So right away, I know that A is going the fastest. What I want to do is compare B and C. So you'll notice here that B and C are both going in a negative direction. They're both going downward. But C has a little bit more of a slope to it. It's a little bit steeper than B. That means C, even though it's going downward, is traveling at a faster speed. So the next fastest would be C, and therefore the slowest would be B, which has the lowest slope. Okay? Or the slowest slope. I don't know which one. But nevertheless, we're looking at the slope is going to tell us the relative speed of these objects. All right, last example here we're going to get, or last two examples we have here is getting numbers wise. So we kind of understand how to read these graphs. Now we're going to fit numbers to it. So this is very similar to what we did in our very first section. These first two problems are looking at distance and displacement given these motions. So you'll see here from this position versus time graph, we have an object starting here at a position of 5 meters. In the first 10 seconds, it goes to 15 meters. So it starts here at 5. And then it goes back to a position of 10 meters. And all I'm doing is just reading the graph at where it's located, okay? Now, if I want to find the distance, what I'm going to do is I'm going to think about the trips that it makes and the distance between those points. So if it started at 5 and it went to 15, what is the distance it traveled? So in that chunk of motion, 5 to 15 would be a distance of 10 meters. Then it went from 15 meters to 10 meters. So I want to think, what's the distance between those? And what I'm going to do is look at over here, the distance between 15 and 10 would be 5 meters. Okay, so in its two chunks of motion, it went 10 meters and 5 meters for a total of 15 total meters for its distance. Now, displacement is different because we want to look at direction. So notice how the first part of motion we know is 10 meters, but notice how it's upwards. So we know that that is a positive 10 meters because it's moving upwards. And in the second part of motion, the line is sloped downwards. So we know it's moving in a negative direction. So that 5 is actually going to be a negative 5 meters. So in total, it moved a total displacement of 5 meters. Okay? Now what does that 5 meters mean? Well, if it started at 5, okay, and it ended at 10, that is only a total displacement of 5 meters. So distance and displacement we can read on a graph by looking at the individual pieces. All right, I want you guys to try example B on your own. So pause the video, find the distance and displacement. You have 3 chunks of motion here, so give this one a shot. All right, so looking at the individual chunks, starts at 1, goes to 14. So that's a distance of 13, displacement of positive 13. Then it goes from 14 to 5, which would be a distance of 9 and a displacement of negative 9. And then here from 5 to 10 would be a distance of 5, displacement of 5. So for distance, I add up all the numbers, get 27 total meters. And for displacement, paying attention to direction, I would get 9 meters. So again, start 1, finish 10. 1 to 10 would be 9 meters in that positive direction. All right, last example, we're looking at the velocity. So in this case, we said before that in order to determine the velocity, we are going to look at the slope of the line, okay? We also know that velocity is simply the distance or displacement divided by the time. So when I want to find the velocity in this case, I'm going to look at, okay, the same thing we just did. I started at 5, and now here I'm going all the way up to 20. So that means I'm going up from 5 to 20. That's a total distance of 15 meters. So I go 15 meters in the time frame. If I go over from 0 to 5 seconds, would be 5 seconds. And I'm reading that down here on the time axis. So if I then take 15 and divide it by 5 seconds, I know that I would get a speed of 3 meters per second. Now what does that mean? I'll show this here in blue, is that I go 3 meters every second. So here's 1 second. I would go up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, and up 3 over 1. It takes me to the end. So that would be my speed. All right, try this one and the last one. So I want you to pause the video, try D. What would be the velocity of that object over that 5-second interval? All right, you should notice it goes down 10 meters in 5 seconds. So dividing those two out, it would be negative 2 meters every second. Okay, now what does that negative tell us? That negative does not tell us it's losing speed, but that negative tells us that it's going in a negative direction. All right, a lot of meat and potatoes in this section, but again, we're looking at the different ways to represent motion, whether it's on a diagram or a graph, and identifying those different variables that we talked about in the first two sections. Got any questions? Write it down. Otherwise, we'll see you in class, babes.